All right, so thermochemistry is technically two topics. It's thermochemistry is a part of what's called thermodynamics, but because we have so many sophomores in here, I cannot teach it as a whole thermodynamics. I have to split it up because you don't have the background to be able to do thermodynamics because you're first year students. So I split it and we do just the thermochemistry part first. And all this means, thermo means heat, chemistry means chemistry, so this is going to be heat of like chemical changes and physical changes. That's what this whole topic is about, heat. Okay, so heat is a form of energy. Now we need to be careful because energy is not only composed of heat. Energy is also composed of work, the ability to do work. Okay, so the total energy of a system in nature is heat plus work. For the sake of this class for energy, we're going to focus mostly on heat. I'm going to briefly discuss work as it pertains to chemistry, but we're not really going to go too much more into detail on the work and really focus on Q, which is heat. But I just need you to know that energy in nature is not just made up of heat. There's also something called work. So let's talk a little bit about work. So consider a gas in this container, right? So there's some sort of gas in here, okay? And there's this little thing right here, it's called a piston, and the piston has the ability to move. So this is not a rigid container. In terms of the container might be rigid, but this piston can move up and down. So you have this gas in this container, and we're trying to like look at, you know, inside the container. And for some reason, this gas is expanding. So work in terms of chemistry is often focused on specifically the gases state of matter. So we're looking at gases for work. Okay. And that is because their compressibility, they're able to expand and compress. And the whole point is that if this gas is able to expand, it pushes against the piston, which is pushing against the atmosphere in essence. So all of the energy, okay, in the form of work, right, this isn't heat, all of the energy from the gas is being transferred to the piston and causing the piston to move. So this would be the gas doing work on the surroundings being the piston and the container. Again, none of that involves heat. So if you can consider the volume change, you can discuss the work that the gas is doing or the energy in form of work that the gas is providing against the piston. And now, a while ago, we used to actually do calculations with this. The pressure of the system multiplied by the change in volume that is allowing the gas to expand or contract equaled the work. And then again, this was work, not heat. And the work is another form of energy. Okay, so notice that as the gas expands, it does work on the piston. Now, if the gas were to compress and it went down, the piston would be doing work on the gas. So the surroundings would be doing work on the system. So we're going to use that word system and surroundings a lot in this chapter. System is the thing we're focusing on, so AKA the gas. Everything else, the container, the piston, the air, the atmosphere, is the surroundings, okay? So the system in this case is the gas, and a lot of times it's not right now, but it would be some sort of chemical reaction. That's our system. We are, and everything else is considered the surroundings, okay? So the whole point is this is a transfer of energy. It's a transfer of work energy, where the energy produced or the work from the system, the gas, is transferred to the piston, and it allows the piston to move up. So a transfer of energy without heat. So this concept does not focus on heat. Okay? Let me see. So now that was the extent I'm going to talk about work. Now we're going to go more into heat, this Q concept. So heat is kinetic energy is the energy of motion, which we talked briefly about last chapter. Now, when I gave you this equation, it looked like this. And it was the root mean square one. Okay, this is the same thing. This is generally how they write it in physics. And the whole point is that mass and kinetic energy and velocity and kinetic energy are directly proportional. If the mass of the object, or if the speed of the object increases, so does its kinetic energy. If something moves faster, it has more kinetic energy. Okay? If the mass of the object is heavier, it has more kinetic energy. Okay? Has more energy because it's heavier, not necessarily moving faster, but because it's heavier, has more kinetic energy. Now, all atoms and molecules that have some sort of mass and are moving, okay, have kinetic energy. And then remember, temperature measures the average kinetic energy of any substance on average. Remember, at any given temperature, all atoms or molecules are not truly moving at exactly the same speed. So what we do is we talk about them as an average. On average, if they're at the same temperature, they have the same average kinetic energy. So we talked about this with like helium, hydrogen, argon. I just threw 3 random gases out there. If they're all at the same temperature and under the same conditions, it doesn't matter their identity. They all have the same average kinetic energy if they're at the same temperature, regardless of who is lighter and who is heavier. Now, that doesn't mean they all move at the same speed, but if this at the same temperature, they will have the same average kinetic energy. Okay? So, let's talk about energy transfer between systems in terms of heat now instead of work. So in these diagrams, you have these 2 different containers. These are called closed systems because they're sealed off, but there's this barrier right here where thermally they can come into contact with each other. So if you look at this initial system, you have one at 350 Kelvin, that's this side. And then you have another one at 450 Kelvin. Oh, he's fine. So here's how they're representing this. I know that they tell you the temperatures down here, but they're showing these arrows as like vectors. The shorter the arrow, the length of the arrow is going to determine the speed. So the shorter the arrow, they're representing by slower moving particles, okay? The longer arrows are representing faster moving molecules. So this should make sense. This container has a bunch of shorter arrows and it's at a lower temperature. So these molecules are not moving as fast because they're at a lower temperature. Whereas these molecules in this second system have longer arrows, which means they're moving faster, and they're moving faster conceptually because they're at a higher temperature. Now, if this barrier right here allows heat to be transferred, now not molecules, but heat to be transferred. If you have a system at a lower temperature and a system at a higher temperature, well, what's going to happen? Well, this system is going to absorb heat, okay? So this system absorbs heat, but, sorry, I don't know why that's sticking like that. Why does this always happen during this period? This system, oh my gosh, I'm going to unplug it. Give me 1 second. So the system 1 absorbs heat, but it absorbs heat because system 2 loses the heat. So that's a transfer of energy. Oh, of course, it's not going to start now. There we go. So this system absorbs energy, but that's because this system loses energy. Now, they will absorb and lose until they're very, very similar, if not identical. Okay, so if you look at this final outcome, also known as thermal equilibrium, you'll see that the arrows all look the same. The temperatures are represented as both the same temperature. This guy lost, this guy gained, and now they're at what's thermal equilibrium. And that's what things in nature will tend to do on their own without any extra input of work. They'll tend to want to reach thermal equilibrium because that's just how the things work in nature. So again, the arrows are these little vectors that represent speed. They look all the same here. Now they're moving about the same speed because they're now about the same temperature. They were able to transfer their heat from the hotter system to the cooler system, okay, until they reached an equilibrium temperature. So last chapter, we also discussed the Boltzmann distribution, and you've actually seen this identical curve on here and temperature. And the whole point is that kinetic energy increases of molecules as temperature increases. And now the average kinetic energy of the particles in a system increases as the temperature increases. So we get more molecules moving faster if we increase their temperature. Now, if we decrease their temperature, the closer we get to 0 Kelvin, now this is based solely on the Kelvin scale, okay? Because the true 0 in temperature is 0 Kelvin. 0 Celsius is not 0. 0 Celsius is just when water freezes. So theoretically, at 0 Kelvin, molecules stop moving. And if they stop moving, they should have no average kinetic energy, because remember, kinetic energy is energy of motion. So you'll see on this chart that as both of them approach 0, that they will have very few molecules in that region. Let's see. Here we go. So look, we have some sort of gas, whoever it is, and it's a gas, let's say it's nitrogen, at 3 different temperatures in Kelvin. So this one is showing, okay, 250 Kelvin. It's your highest one because you have the most molecules. Here's your most probable spot right here down the middle. At the lowest average kinetic energy because they're the coolest molecules. So then you go to 500 Kelvin. Now notice that the peak drops. However, the curve widens, which means the area under the curve is still considered to be the same. But it's shifted. So now we have way more molecules probable of having higher average kinetic energy because they're at a higher temperature. So the higher the average kinetic energy, or higher average kinetic energies correlate with higher temperatures. And then, of course, the reverse is true. So then you look, you have the highest temperature of the 3. Look how many molecules or atoms, depending on who the substance is, I guess. Look at, this is the most probable region, right? They have the most molecules moving at higher speeds because they're at higher temperatures. Or sorry, not higher speeds. They have higher average kinetic energy, which also correlates to higher speeds. Okay, so we've already discussed this last chapter. It's the same concept. Again, this curve has the lowest peak, but it's also the widest. So the area under the curve is said to be comparable. Okay, so the nature of energy, and we're going to talk about this in terms of heat. So we're going to kind of forget about work now. Okay, we're going to focus just on heat, and heat is represented by the letter Q. And heat is the transfer of energy between 2 objects due to a temperature difference. So one thing might lose heat while the other thing gains it. Now, heat is an extensive property. And if you don't remember, an extensive property means the amount of stuff you have matters. Meaning, heat will change if you have more stuff, and heat will change if you have less stuff. So heat, which is an extensive property, will change based on how much stuff is present or not present for that matter. Heat is generally measured in joules or can be converted using the metric system to kilojoules. We talked about this last chapter. I don't need you to memorize this, but if you have vague memories, on your equation sheet, you'll see this R constant. It looks like 8.314 joules per mole Kelvin. And now we use this because, or I showed you this last chapter because when we did this equation, the root mean square for speed or velocity of gas molecules, it was this equation, and that was the R constant we used. But when we talked about speed, we wanted to talk about speed in terms of meters per second, so we kind of just rewrote it with the joules replaced with this so it could make our units look better. But again, this is truly a joule, and a joule is the most common unit of energy for chemistry, a joule or a kilojoule. Okay. Other forms of energy that you're used to hearing about are calories. So these are like the energy in your food. Okay. And by definition, a calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So what this means, this is your conversion factor. You don't have to memorize it. Every time on the AP test they've asked you to use it, they give you this. So if you find your answer in joules and they say, hey, convert it to calories, and then they give you this conversion factor, you just need to know how to use it. So what this means is for water, to change the energy of water, you have to put in 4.184 joules to change 1 gram of water 1 degree Celsius, and that's known as a calorie. Now, a calorie in this instance is kind of interesting. It's represented by little baby lowercase c. And it's actually not the same calorie that's on your food labels. So on your food labels, when you see that something's like 30 calories, it's not these calories. It is not those calories. It's actually kilocalories. So if you want to talk about it in terms of these calories, it's 30,000 of these calories, okay? And I know that seems like a giant number to you, but your food labels are all in kilocalories. So why do you think they do that? Well, okay, if something is 30 calories and you have to put it on a food label and it's really 30,000 of these calories, they're going to have so many numbers and so much stuff on the labels, right? Some things are 300 calories, 400 calories, right? They'd have to be writing 400,000 on labels and things like that. So they don't, and they just rewrite them as kcals, and they don't really tell you that. The way that you represent a kcal instead of calling it a kcal is they just write calories with a big capital C instead of a lowercase c. So I don't necessarily need you to memorize this. I'm just telling you that your food label are not these little baby calories. They are these calories down here, okay? So let's talk about specific heat capacity. So specific heat capacity is represented by the little baby variable c, and the specific heat of any substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. And its units are joules per gram Celsius, or you can call them joules per gram Kelvin, and we'll talk about why in a second. Okay, these two units are interchangeable. I'll talk about why later. Okay, so for water is 4.184 joules per gram degree Celsius. That's its specific heat of water in the liquid phase. So what does that mean? That means it takes 4.184 joules of energy to change 1 gram of water by 1 degree Celsius. Okay, now every single substance has its own specific heat, meaning silver's specific heat is not this number. Copper's specific heat is not this number. Argon's specific heat is not this number. Lithium's specific heat is not this number. They belong to every single substance independently. So sometimes you will be asked to calculate C given a whole bunch of other information, but generally C's are constants that you look up in a chart or in the back of a book or somewhere, okay? So you don't have to memorize them. The only time you would ever not memorize them is if you're asked to calculate them given other data. Okay, so the whole point of C values, these specific heat capacities, and how they are different for each substance is because you can add the same amount of heat to two different things and observe wildly different temperature changes. Now, we're going to talk about the difference between heat and temperature in a minute, but not yet. So think about this. I heat up a bucket of copper for 5 minutes, and there's 10 grams of it, okay? And I heat up a bucket of water, 10 grams of it, for 5 minutes. So same amount of time I heat it up, same amount of heat I'm putting in, and the same amount of each substance, same amount of copper, same amount of water. Which one would you rather have thrown on you? I mean, if you had to choose. I'll wait. You want the copper thrown on you or you want the water? Okay, so Martin, very good. So most likely the water, but why did you pick the water? If you're heating them, putting the same amount of heat for the same amount of time, why would you prefer the water to be poured on you as opposed to the copper? So let's talk about metals. What do we know about metals, for example? They're very, very, very great conductors of heat and electricity. You probably already know that. But there's something else about them that we're going to learn. They have really, really low specific heats. What does that mean? Well, let's look. Here's a chart of different substances, different specific heats, and you'll notice that you've got a bunch of metals down here that have pretty low specific heats, okay? So what does a low specific heat correlate to? So low specific specific heat. Low specific heat, so these little small c values. That means, let's see for iron, 0.545 joules per gram degrees Celsius. It means it only takes 0.45 joules of energy to change 1 gram of iron by 1 degree Celsius. AKA, they change temperature without a lot of work. You could have a huge temperature change with a lot less work than it would take for, let's say, water, which means if it changes temperature a lot easier, it's gonna get hotter quicker, which means you would probably not want to touch the metal after that amount of time if you had to choose between the water. Now, I realize that 4.18 or 4.184, please notice these are just abbreviations. This is just an abbreviated version. Doesn't look like a big number for water, but it is pretty big, like relative to our metals down here when you see them. Your metals do not take a lot of energy to change temperature, and that's what low specific heats relate to. So let me see. And then again, of course, we're assuming under like the same conditions, like you're applying the same amount of heat. Okay, so low specific heats relate to not a lot of energy being put in to change it by 1 degree Celsius. So your metals get hot very, very easily. They don't require a lot of work to get hot, which we know that's why they're good conductors of heat and electricity for other reasons. So let's calculate some numbers with a heat equation. So if you check out your equation sheet and you go to the bottom, thermodynamics and electrochemistry. So we're technically doing thermochemistry, but it's part of this chapter. We have an equation that has heat in it, and it's Q equals MC, and that triangle is a delta T, and that triangle means difference. We'll talk about it in a second. And then again, all of what those letters mean are over here. Q equals heat, M equals mass, C equals specific heat, and T equals temperature. So this is often referred to as MCAT, just because that triangle kind of looks like an A. But just so you know, that triangle is the Greek symbol for delta. And delta in math, any sort of mass, means change. And change for us is going to be final whatever minus initial whatever. And so if it's delta T, it's final temperature minus initial temperature. If it was delta M, it'd be final mass minus initial mass. Excuse me. If it was delta V, it'd be final volume minus initial volume, and so forth. Okay, so again, M is the mass, and the mass is going to be grams for right now. C is the specific heat. This is usually a constant, okay, so you can look it up. And then T is some sort of temperature change. Now, this is going to bring me back around to this whole idea that I told you that the units for specific heat could be joules per mole Kelvin or joules per mole Celsius. So I need to prove something to you. Last chapter, we were only allowed to do temperature in Kelvin. And the reason that is Pervner, PV equals nRT, right? This is the only spot for Kelvin. So this is the only chapter all year long that you get to use temperature in Celsius. All year. This is the only time. Every other chapter we will always do temperature in Kelvin. So just be very, very careful with that, okay? And I'm going to prove to you why. So we're going to calculate delta T, just delta T, and I give you an initial temperature and I give you a final temperature. So you do what? You do 78.2 final minus initial, and you get 58.2. Now, what would this be delta T if it was in Kelvin? Well, what's 78.2 in Kelvin? So 78.2 plus 273, 351.2. Minus so final, minus what's initial? Well, 20 plus 273 for Kelvin. Oh, what do you get? Anybody? The same exact number. The subtractions change with the same magnitude. Do you remember where you've seen this before? Do you remember that question on the multiple choice test that I gave you 10 Celsius and 20 Celsius, and I asked you for the temperature change in Kelvin, and a lot of us got it wrong? This is that concept showing back up again. When you subtract Celsiuses from one another, and then you also subtract their Kelvin versions of one another, you still end up with the same exact magnitude of change. So the point is it doesn't matter whether you use Celsius or Kelvin in this chapter only because we're subtracting them. Are there any questions? So that is why for the specific heat constant, it can be joules per gram Celsius, or it can be joules per gram Kelvin, and there's no like conversion between them. These are synonymous with one another for your specific heat constant. Okay? All right, so let's keep going. So we're going to do a calculation. So this time we're asked to calculate the specific heat. So let's go through this. Specific heat, what letter is that? That's C. 10 grams, that's mass, right? An unknown substance, so we don't know who the substance is. This is not molar mass, this is mass, little m, not big M. This is 114 joules of energy. So this is Q. Joules is heat or energy in this chapter. And then I give you an initial temperature and I give you a final temperature. So Q equals mc delta T. You're asked to solve for specific heat, so you rearrange and divide both sides by mass delta T, and so this is the equation you just plug and chug into. So Q is 114 joules. The mass was 10 grams. And then the delta T is 50.4, that's final, minus initial, which was 25, sorry, I ran out of room, degrees Celsius. And you should be getting 0.449 joules per gram degrees Celsius. I'm going to give you a second to do that, please. All right, any questions so far? So what could happen now is if you do this calculation for specific heat is I could give you a table full of a bunch of specific heats and I say, well, based on your calculations, who do you think this substance is? And so 0.449, so we would look at this table. 0.449 is definitely the closest to iron, so this substance, based on our calculation, is likely to be iron because that is the specific heat for iron. Questions? Okay, let's try another one. A piece of metal, and I give you a mass. Oops. A mass, so M. And I tell you it absorbs 256 joules of heat, so this is Q. And then I say its temperature increases by 425. This is important. What does this mean? Increases by. Notice you don't see a final temperature and an initial temperature. So what is this meaning? Increases by would be the same thing as like changes by, decreases by. I mean, I know this is increasing, decreases by. This is your delta T. You don't even have to calculate delta T. They are giving it to you in this wording. Good job, guys. So you have M, you have Q, you have delta T. What's the specific heat? Well, you rearrange. So Q equals mc delta T. We're solving for a specific heat. That's this guy. So it's Q over m delta T is specific heat. So the Q is 256 joules divided by the mass is 4.68 grams. Sorry, I know I kind of ran out of room. And 425 Kelvin. and you end up with 0.129, and then it's joules per gram Kelvin for your units, which is the same thing as joules per gram degrees Celsius in this chapter. Any questions on that? And so you get 1.29, and I say, okay, well, here's the chart. Who would you guess that this material is based on its specific heat? And that one definitely is the closest to lead, which is 0.13. How are we doing? Any questions before I move on? Okay. So in this class, so there's multiple ways to discuss potential energy. In this class, we will discuss potential energy in the terms of chemical bonds, because all bonds within compounds and molecules and things like that have potential energy stored in them. So think, for example, when you go to eat food, right? The food is made up of a bunch of different chemicals, molecules, okay? It has energy stored in the bonds. So you eat the food, which means you're literally manually breaking down the bond. Well, you're breaking down the food, and then your body takes and metabolizes it and breaks the chemical bonds and takes the energy that it needs for it to do all sorts of things in your body. So it takes that energy to do work. Okay, this is like all full circle. Now, potential energy in real life is not just stored in bonds, right? So this is a perfect example of just like another real life application. So you have a dam here, okay? And behind the dam is a bunch of water, okay? Is a bunch of water. And the water is not moving very fast behind the dam, so it has low kinetic energy, but it has a ton of potential energy just sitting behind there, okay? Now, what happens is that water will eventually flow through the dam, through these openings, and its potential energy gets converted to kinetic energy, okay? Which means that water starts moving really, really, really fast through the dam, okay? Anybody know what the point of dams are, or what's one way that they use them? So they take this water, and this water is used with all of this energy to power or move turbines. Okay, they're these machines that can do, what's one thing they can do? Provide electricity. So they're literally using stored water back here to go through here. It moves super fast, powers the turbines, and the turbines have the ability to do work and provide electricity for like cities. Okay, so this is a way that they took the stored energy and converted it into being able to do work. Okay, so let's discuss the whole concept between temperature and heat, because they are not the same thing. Temperature is an intensive property, meaning how much stuff you have. The amount of stuff you have is irrelevant. So think about it. 50 grams of water at 100, that's its temperature. 5,000 grams of water at 100, that's its temperature. So we have different amounts, but they're at the same temperature. I don't care. 100 is 100, okay? Also remember that the temperatures that measure the average kinetic energy of any sort of atoms or molecules in a system, and that average kinetic energy and temperatures directly proportional. So if you double the temperature in Kelvin, you double the average kinetic energy. If you decrease the average or the temperature in half by Kelvin, you decrease the average kinetic energy by half. So they're directly proportional. Now, let's talk about heat and temperature. So heat is extensive, meaning how much stuff you have matters. Heat will change with more or less stuff. Temperature will not. 100 degrees Celsius is 100 degrees Celsius, okay? So let's talk about these two things. I give you a drop of water at 100 degrees Celsius, and I give you a bucket of water at 100 degrees Celsius. They are at the same temperature. Which one would you rather have poured over your head? The drop or the bucket? So water boils at 100, right? So which boiling water, they're both boiling. Which one would you rather have dumped on your head, right? It should be the drop, but the question is why? Well, because the drop of water contains less heat because there's less of it, right? Extensive. The bucket of water contains more heat. Why? Because there's more of it. They're both at the same temperature, but the bucket of water has way more heat because you have more of it. So while temperature is an intensive property, how much stuff you have matters for heat. Okay, so we've sometimes used them interchangeably. So I'm trying to kind of like bunk this myth that they mean the same thing. They really, really don't. You can have things at the same temperature but have totally different heat content. Okay, so again, a few of the words we've been using in the chapter and we'll continue to use is system and surroundings. So again, the system is everything we're focusing on. So in this container, it'd be this thing inside the container. So this would be my system. The surroundings is literally everything else. The piston, that's this thing right here. The cylinder, the room, you, me, everybody else. So the system, so this is like just a container with gas molecules in it. If we're doing a reaction, the reaction is the system. Okay, there's a couple different types of system. We briefly discussed a closed system when we talked about thermal equilibrium. So look, at a closed system would be a system where the molecules can't come in or escape, but heat can be transferred. An open system means heat can leave, heat can come in, but so can molecules. Molecules can leave and come in. And then an isolated system allows very little or minimal heat transfer, as well as molecules or particles are not allowed to escape. So it's a closed system with no heat transfer or minimal heat transfer. Okay, now this slide might be familiar to you from accelerated bio. Okay, internal energy. Now remember, I'm showing you this slide because energy is really work and heat. Okay, again, we're focusing mostly on heat. So because energy is work and heat, if you have a negative E, now remember there's no such thing as negative energy. The negative is descriptive. What it's telling you is where the heat is going. Heat is leaving, exiting, leaving, exiting, being released. All those mean the same thing. From the system to the surroundings. Heat's being given off. Okay? And because this is all energy, which includes work and heat, they call this exergonic. Okay? Now, if delta E, delta E is positive, okay, that means plus, like you're adding heat. Heat is going in. Heat is being absorbed from the surroundings into the system. So they call this endergonic. Heat's going into the system from the surroundings. So it's like taking heat and putting it into it. So in this class, though, sorry, I should have done this first. First law of thermodynamics states that energy is conserved in any process. It's the same as law of conservation energy, meaning energy can either be created or destroyed. It can be transferred, moved around, rearranged, okay, just like this is the law of conservation of mass. But you can't just get energy out of nowhere and it can't just disappear. Like it can go from one place to another, but it doesn't just appear out of nowhere and it doesn't just disappear out of nowhere either. Okay, so for this chapter, we'll be focusing on the energy of system changes during chemical reactions that either produce heat or absorb heat, as well as phase changes. Now, phase changes are not chemical changes. Phase changes involve a heat exchange, but the substance themselves do not change their identity. So we'll talk about phase changes as well, okay? Because phase changes involve heat. They just don't involve a changing of chemical like chemical reactions do. Okay, so again, when we talk about energy in terms of heat, we have different words for them. So in bio, right, you called this endergonic. and you called this exergonic. Okay, now we're focusing solely on heat. So this is Q. This is not heat and work. So when we talk about heat going into a system and heat leaving a system, going into a system with heat is called endothermic. Okay, the thermic part is the heat part, and the endo is kind of like this guy, right? Into. And then heat only, not full energy, heat only leaving a system is called exo, like exiting, thermic, heat exiting. Okay, so again, we don't call it this endergonic and exergonic because we're not considering work right now. We're just considering Q heat. So the surroundings are like us. Okay, this is where we are. So if heat goes into a system, this would either be your phase change, I'll put PC for phase change, or your chemical reaction. If heat goes into the system, right, and we are the surroundings, we are always the surroundings. This would feel cold to us, right? If heat's moving away from us into the system, to us, the surroundings, it would feel cold. If heat is being given off or released by the system to the surroundings, and we're in the surroundings, we're going to feel that heat. So to us, this would feel hot. Now, here's a very, very big misconception. You go do a reaction in a beaker and you put your thermometer in it. What is your thermometer measuring the temperature of? The system or the surroundings? Take a guess. You got a 50-50 shot. You put a thermometer in a beaker. And you're like, okay, I'm doing this experiment. Like, oh my gosh, it is getting hot. My thermometer is jumping in temperature. What am I measuring? So I'm glad that you guys put that because that is probably what everybody thinks is that you're measuring the system. You are always measuring the surroundings. Your thermometer is not inside of the chemical reaction. It's inside of the beaker that has a chemical reaction happening around it. You cannot stick a thermometer inside the molecules. Okay, so whenever we measure temperature, we are measuring the surroundings always. Please note that down. Please, please, please note that down because that is a super big misconception because you think if you dump chemicals in a container and you put your thermometer in it that you're inside the chemicals. You are not inside the chemicals. You are inside the container that is holding the chemicals. Okay? So, okay, along with heat in this chapter, we have something called enthalpy. And enthalpy pretty much is heat, which is Q, but considering moles, which is how much stuff we have. And now enthalpy is represented by delta H, okay? So before we had heat as this, right? Oops, sorry. This one. This was one equation we have for heat. This is another equation we have for heat, where heat equals moles of how much stuff you have times its enthalpy. Now, it can be mass times enthalpy if the enthalpy is measured with mass in its units. It just depends on which one you use, okay? So look at, you take this reaction, you have hydrogen and oxygen in a balloon. Now, if you don't already know this, which we have talked about it, hydrogen and oxygen in large components is highly combustible. So this is what they put in the Hindenburg, which is why the blimp blew, like it literally did this. It blew up, okay? So we can measure the enthalpy of a system if we know how much heat was produced and how much hydrogen and oxygen in terms of moles were inside the balloon. Okay, now if you look at this, this looks like it's blowing up to me. If you were standing right there when this happened, do you think this would feel hot or cold to you? Probably hot, right? Like you literally have a flame coming at you. So this is hot, meaning this reaction is considered to be exothermic. It is releasing the heat to the surroundings, which is where we are, okay? So this is an example of an exothermic reaction. So let's talk a little bit more about enthalpy. So the sign changes for enthalpy are this. If delta H is negative, the reaction is exothermic. Just like when delta E was negative, the reaction was exergonic. Okay? Again, this E though has heat and work in it. This is only focusing on heat and moles. Okay. I shouldn't put plus. I'll just say heat and, oh geez, I'll just write the word and moles. Okay, so negative H is very similar to a negative E, but we don't call it exergonic, we call it exothermic. Heat being released, lost, given off. Okay, that means if delta H is positive, heat is going into, being absorbed. This is kind of like endergonic, right? But it's not gonic because we're kind of not focusing on work. So we call this endothermic. We're focusing on heat only going into some sort of system. Okay? And again, this is enthalpy because we're talking about heat with the moles taken into consideration. Okay? So let's predict the signs of the enthalpy change. So what is enthalpy change? Change is a triangle, enthalpy is H. That's what this is. And the following process is carried out under a normal atmosphere and indicate whether the process is endothermic or exothermic. So an ice cube melts. Which way does the heat flow if an ice cube melts? What causes the ice cube to melt? Is heat being released or is heat being absorbed by the ice cube? Heat should be going into the ice cube to cause the ice cube to melt. So going into the system is a positive H. A positive H is endo, heat going into, thermic. Okay? What about combustion? 1 gram of butane, so butane is lighter fluid, is combusted. So combustion, do you think is going to feel hot or cold to you? If something combusts in your face. Definitely exothermic. Okay, so heat is given off. So this is a negative delta H. Heat is given off. It is lost. It is released. Okay, exo, it exits. It leaves the system. Okay, and just so you know, and I want you to write this down, all combustion reactions are exothermic. I will repeat that. All combustion reactions are exothermic. Okay, so let's keep going. Don't let these next few slides freak you out. Okay, so enthalpy is heat content of a system, like it's H with moles considered. Okay, it's an extensive property, meaning how much stuff you have matters, which is why moles come into play. Now, there's different ways you can write H. There's tons of different ways, okay? All they're trying to do here is they're trying to be specific. So this would be like the enthalpy of a reaction. The RXN just means reaction. Okay, this would be the enthalpy. And then the reason they write this here is because they're telling you that this reaction is combustion. They're just trying to be descriptive or specific, okay? Where do you get these H values from? Well, there's two ways. One is you can solve for them if you know Q and mole. For right now, there's going to be other ways. The other way you get H's is by looking them up in a chart, okay? There are set values of H's for different things. Like there are set enthalpies of combustions for different organic molecules that combust. There are set enthalpy values for water, which we'll talk about in a second. So these are like for the energy or the heat involved for chemical reactions. Now, heat is not only exchanged in chemical reactions. Heat is also exchanged in phase changes. So when I talk about phase changes, I'm talking about solid to liquid. Liquid to solid is a phase change. Okay, right? Liquid to gas. Gas to liquid. Okay? These are phase changes, meaning there's no chemical reaction going on. The identity of the substance doesn't change, but that substance is either absorbing or losing heat. So because of that, they have enthalpy values. So if you see this little VAP down here, we're talking about vaporization. Well, what does vaporization mean? It means to evaporate. That means you're taking something from a liquid and turning it into a gas. And there is energy involved in changing a liquid into a gas. And then there's another one, right, that they call it the enthalpy of fusion. Now, this is solid to a liquid. So where do they get this word fusion? So this is melting, right? To get something to melt, it has to take in heat. It has to absorb heat. So where did this word fusion come from? Well, it came from the fact that if you take two metals and you want to fuse them together, you heat them up and you melt them to get them to fuse together. So that's where they got this word fusion from. Fusion is just a fancy word for melting. Okay? So let's keep going. Sometimes, and actually very often a little bit later in the chapter, you're going to see standard enthalpy changes. This word standard is what allows you to draw this little circle right here. And this little circle, all it means is it's a set of conditions. 1 atmosphere and 25 Celsius, aka room conditions. Okay, now do not confuse this with STP. Okay, STP is 1 atmosphere, but it's 0 Celsius. Hardly any sort of room anyone would want to do an experiment in. Nobody wants to sit in a room at 0 degrees Celsius. So when they have all these standard values, it's because they've done them under standard conditions of like a normal laboratory setting. Like your room right now is probably approximately this. Very, very close. Okay, so that's what that little circle means. That's what that standard means. So it does not mean STP. Okay, now heating and cooling curves. So that's what we're going to move on to. We're going to start investigating stuff being heated and stuff being cooled. You can read this later. I'm going to show you this curve. Okay, we're going to start getting really good at drawing these. So here's how this works. This is your temperature that you're at, and this is your different states of matter. We're doing phase changes, right? We're not changing chemicals. So this is like its solid form, its liquid form, and its gas form. And I'm going to use water as my example, but you can do these curves for any kind of substance. You can do it for silver. You can do it for ammonia. You can do it for methane. You can do it for whatever you want, okay? This number, this plateau down here, see where this goes flat? This is the substance's freezing point. Freezing point. And if we're looking at water, that number is what in degrees Celsius? What temperature does water freeze at in Celsius? If you did not know it was 0, you do need to know that now. Sorry, I'm trying to draw a straight line. So I'm drawing it from my plateau right here. This is the boiling point of the substance, and for water, that's going to be 100 degrees Celsius. So the whole point is that if you're below the freezing point, you're solid. If you're in between the freezing and the boiling point, you're a liquid. If you are past the boiling point, you are a gas. And then it shows you kind of the particles. Solids are compacted, liquids are less compacted, and gases are fully apart. Question so far. Now, what's interesting is these plateaus, okay? So, melting to freezing or vice versa. The actual process of melting or freezing, and the same as boiling or evaporating to condensing or condensation. You should notice that as you're moving along here, you're increasing temperature. If you're moving down, you're decreasing temperature. Same with all of these. Increasing temperature, decreasing temperature. Increasing temperature, decreasing temperature. But as you move along these lines, there is no temperature change. And this is a concept that is very confusing to students. You go, well, why, how come if I'm melting, there's no temperature change? Because you know there is heat involved, and that is true. But there is no actual temperature change when you have both states of matter present. Okay, until all of the solid has been converted into a liquid when you're melting, there is no temperature change. So then you go, well, in order to get the solid to turn into a liquid, it has to be absorbing heat. And you are right, it is absorbing heat. So the point is what is the heat doing if it's not changing its temperature in this part and in this part? Anybody know what the heat is doing if it's not changing its temperature? So I don't expect anyone to know this concept, but I'm using water as my example, right? What holds water together? Water molecules, what holds them together? It's the attraction, right? The hydrogen bonding. Water molecules are attracted to each other through hydrogen bonding. Oops, let me change that. Okay. So what is happening on the molecular level during melting or freezing, as well as boiling or condensing, is, well, let's do melting and freezing first. What's happening on the molecular level is the heat is coming in and weakening these intermolecular forces. And instead of the solid now being super close together, it's causing the water molecules to spread further apart. Ooh, I drew that one bad. Okay. I'm not the best artist. Okay. So what it's doing is the heat is weakening the forces. So now these molecules are becoming further and further apart, which is what makes them turn into liquids, okay? So just this part right here involves the weakening of intermolecular forces. So what happens here? Here, when you boil, you literally break all intermolecular forces holding the molecules together so that they can be so far apart that they're not really attracted to each other. That is the point of boiling in the gas state, is that the gas molecules end up spread so far apart that you've completely broken any forces holding all molecules together. But that's why the temperature doesn't change. The temperature doesn't change is because that energy goes into weakening here, weakening here and fully breaking here. Okay. Sorry, my thing is going crazy again. All right. Sorry. This thing is quite a pain. Hello. Okay, there we are. So again, all of these lines are going to have equations that correspond to them, whether temperature is changing or not, temperature is changing or not, temperature is changing. Okay. Questions on this so far? Oh, I see a bunch of. So, okay, so I just want to be clear. You're not actually breaking the water molecule apart. You're breaking the forces that holds water molecules together. So like you're not ripping the hydrogens off of the oxygen. You're messing with the interaction between different water molecules. Okay? So if we go to the next slide, and I'm not going to stay on this slide very long because I'm going to show you this slide back on our chart, okay? Every single line on that phase change diagram has an equation that goes with it. So let's talk about it. We're going to go backwards. I'm going to reset this. We have two equations now for heat. Q equals MCAT and Q equals NH. Okay, these are our two equations. This is the only one on the equation sheet, aka you need to know this one. So let's look at it. MC delta T, where is temperature changing? Well, temperature is changing along the solid line, it's changing along the liquid line, and it's changing, right? Because this is temperature right here, right? So we're moving up, we're moving up, we're moving up, or you could be moving down, moving down, moving down, okay? So all of these lines would have MCAT associated with them. So this is Q equals MC delta T right here. This is Q equals MC delta T right here. This is Q equals MC delta T right here. Now, the reason you see all those little letters is because, believe it or not, the specific heat constant changes with your state of matter. So like specific heat for water in the solid form is actually not the same as the specific heat for water in the liquid form. So I put the specific heat for the solid down with the solid, and the specific heat for the liquid with the liquid, and the specific heat for the gas up with the gas, because they're actually different numbers, okay? Now for this line, for these lines right here, we have Q equals NH. Why do we use this equation? Well, because this equation involves a temperature change. There is no temperature change here. So we're going to call this Q equals NH. This also could be called M for mass H, but I'll stick with the NH, okay? This could be Q equals MH. How do you pick? Look what your H value is. That's what will help you pick. Look what the constant is, okay? So what does all this mean? Well, this means if I want to calculate heat associated with different phase changes, I am going to have to incorporate these equations depend on what I'm doing. So we're going to do a practice problem. What time does the bell ring? Can you guys tell me?
Like 11:09 or 11:08.
Okay. So this is a cooling curve, right? This is just the opposite of a heating curve. You start at a hotter temperature and you get cooler and cooler until you turn a gas into its solid. It's just the reverse of a heating curve. Okay, so we're going to do number one now. I'm going to keep recording. I will tell you, that you can leave, but I'm going to keep recording so that I can have all of this up. Well, at least 1 and 2, and then I'll have 3 up, but you can head out after we finish number 1. You can also hang around if you want to go over number 2, but you need to watch this video once I post it, okay, so that you can understand how to do all 4 of these problems. So here we go. How much energy, so this is Q, is needed to heat 25 grams of water? So we're using water as our substance, and we're heating it from 20 degrees Celsius to 60 degrees Celsius. So this isn't a chemical reaction, this is a phase reaction. We're just taking water and we're heating it, okay? So it's not going to change chemically. So what do? Well, first thing you do, draw the lines. Draw your chart. Here it is. Okay, it always goes up, over, up, over, up. And this first flat line is always the freezing point, and because it's water, it's 0. This flat line is always the boiling point, and because it's water, it's 100. Then what I like to do is I like to draw dots about where I think 20 is. So like, maybe here. And then 60 is like, about here. And then you take and you start at your first dot and you draw a line to your second dot, or an arrow. You're going from 20 to 60. Okay? So you go, okay, well, what's the equation for this line? Did I even change states of matter? No, I stayed completely in the liquid range. I'm in the liquid range. So the equation for a changing temperature is the equation that has changing temperature. Q equals MC delta T, changing temperature. Now, I'm going to put C as a liquid because in this range, water's a liquid. Okay? So now I'm going to go back. If you move forward in the notes, you will see at the end of these problems, I put down a bunch of the constants for water. So like these are numbers that you would plug in. No, you don't need to memorize them. You just have to know how to use them, okay? So here's the specific heat for liquid water. It's this number. So I'm gonna go back and plug that in there. Oop. So Q equals, the mass was 25 grams. Specific heat of liquid water is 4.184 joules per gram degrees Celsius. Again, I just looked this up on that slide. This is on the slide. You can look it up. And then delta T is final temperature, so that's 60 minus 20, final minus initial, degrees Celsius. So let's look at our units. Grams, cancel, Celsius, cancel, and you're left with joules. This is a constant. You never look at it for sig figs. This ends up being 40.0. This is 3 digits. This is 2 digits. So your answer is 2 digits. So let's give me a 2-digit number. I think it is this if I remember correctly, but I'll wait just to be sure. Is it 4,200? Sweet. Okay. Which, if they asked you to convert it to kilojoules, you would divide by 1,000. It'd be 4.2 kilojoules. Now, this is what I'm going to end with for class, but I'm going to keep going, remember, on my lecture, on my notes, because I'm recording already. Notice this number is positive, okay? Well, what does a positive Q or positive H mean? It means you're putting energy in to the system, which means this is endothermic. Anytime you are climbing up the hill, the process is endothermic. Heat is being absorbed. Where is it being absorbed from? The surroundings. Okay, so if you take a pot of water and it's at 20 degrees Celsius and you put in enough heat, specifically this much, you can turn the 20 degrees Celsius water into 60 degrees Celsius. In real life, how would we do this? Well, we'd probably put it on a stove, right? And the water would absorb heat from the stove, okay? Questions so far? All right, so I'm gonna pause this. All right, so we just finished the first one, an endothermic problem, which means heat was going into the system, okay? So we're going to work on the next one, the second one, which is going to require a little bit, well, actually a lot more work. So it says how much energy is needed to heat 25 grams of water, so still water, from 20 degrees Celsius to 120 degrees Celsius. So let's go ahead and draw our phase change diagram. Oops, I didn't want to use that color. So you draw the box, right? Okay. And we're still doing water. So up, over, up, over, up. And water freezes at 0 Celsius. And water boils at 100 Celsius. And I already forgot, was it 20? Okay, so 20 to 120. So, oops, I went too far. Wait a second. Okay, so 20 is going to be like right here, and then 120 is going to be up here. So you might just initially think, well, why can't we just use MCAT, MC delta T? Why can't we just plug straight into there? Well, the reason you can't do that is because you are going through a phase change. You are starting with liquid water and you are ending with water in the gas form. So you do not get to just plug into MCAT and call it a day. So here's the trick. You start with your first dot, which is at 20, right? And you draw arrows. At every intersection you meet, you end the arrow. And then you start another one. and then you go to another one, and then remember this is 120. So what this means is every arrow you have to draw is how many equations you have. So now you have to know which equations go with which part. So this right here, this line right here, is Q equals MCL delta T. That goes right there. Plus, so these are additive. Q equals, what's this line? This is NH or MH, depending on what you do. So H, vaporization, right? Because liquid to gas, right? This is solid, this is liquid, this is gas, is evaporating. Plus, we still have one more. Now this is temperature changing again, so I get to use MC delta T, and this would be the specific heat for gas. I highly recommend calculating all of these guys out separately. So like 1, 2, 3, and then add them all up. Do not round until the very end. So I'm going to do number 1 first. Okay, so the mass of the water, I'm going to have to go back. The mass of the water was still 25 grams. Okay. So 25 grams. And then I remember the specific heat of liquid water, but you can look it up on a couple slides ahead of this, 1.184 or 4.184, excuse me, joules per gram degree Celsius. Be very careful right here. Delta T. Delta T belongs to this arrow only. So where does this arrow end? That arrow ends at 100 minus 20. Okay, it started at 20. It is not the full 120 minus 20. It is for just this arrow because this equation is for just this line. So I would calculate that out. Now, I'm going to do number 2. That's this one. Let's see, I'll do that up here. Number 2. Oh, that's not enough room. All right. N stands for moles. Well, I didn't give you moles. I gave you grams. So you have to turn 25 grams into moles. So this whole thing right here is N. Okay, there's your N. Now, enthalpy of vaporization. So again, I'll show you. It's 40.8, but I'll show you where you can find it. Enthalpy right here of vaporization is 40.8 kilojoules per mole. That's for water, right? Which is what we're working with, water. So I'll go back. Oh, wrong one. So this is 40.8 kilojoules per mole. Now I told you before that you technically could do mH, and you would do that when they give you like kilojoules per gram, and then you can just leave the grams. It wouldn't be necessary to convert to moles. So this is your N, this is your H, vape. Now here's the hard part. Well, it's not hard, but if you look over here, this should have been degrees Celsius. If you look at the units, Celsius cancels, gram cancel, and you're left with joules for this first equation. So this first equation will come out in joules. Now your second equation will come out in, look at moles, cancel, gram, cancel. Your second equation will come out in kilojoules. You can't add joules to kilojoules. I am making the choice to convert this one to joules. You could just as easily convert this one to kilojoules. It does not matter unless the problem specifically asks for a specific unit of energy. So I'm going to say, okay, 1,000 joules in 1 kilojoule. Whoa, I did that wrong. 1 kilojoule, right? Kilojoules have to go on the bottom, is 1,000 joules. And that will leave me now with a joules here that I can add. Okay. And then let's see, number 3. Let's see, what color shall I do that in? Let's do it in green. So this is MC delta T. So number 3. Oh, I don't want to do orange. So the mass is still 25 grams. Now, this is the specific heat of water as a gas. So if you go back to my constants, which you don't have to memorize, the specific heat of water, right, these are all for water, as a gas, is 1.87 joules per gram degrees Celsius. Oops. What am I doing now? So 1.87 joules per gram degrees Celsius. MC. Now delta T. Now be careful, it only is the delta T that belongs to this arrow. So the final temperature of that arrow is 120, while the initial temperature of that arrow was 100. It was not 20. This arrow starts right here, okay? So I highly recommend calculating these out separately. Calculate this one out, calculate this one out, calculate this one out. I'm going to do that. I'm going to pause this video until I have all three different numbers. Right, so I have my three different equations. So all you're going to take is the numbers. Remember, you do not want to round until the very end. 8368 joules plus, and then I have, ooh, this is a big number, 56603.77 joules plus 935 joules, and we get, I don't know, it's a huge number though. Okay, so you get like something like 65898.77 joules. Now, I'm going to go off of the masses. I know it can get confusing, but let's just do 2 sig figs, okay? So this would be 66,000 joules or 66 kilojoules. So notice this number is positive, meaning this process is endothermic. You have to put this much energy in if you want to change water starting at 20 degrees Celsius and heat it up to 120. Now I want you to notice this term right down here relative to, like, let's say the first one, the pink one and the blue one. Look how huge. So this is a joule, right? That's not a 5. This is a joule. Look how huge this number is to vaporize. This is a huge number. And the reason that is in order to vaporize, you literally have to completely rip water molecules away from each other to turn them into a gas. That requires a lot of energy to do that, okay? So that's why you see this term be so big, all right? You're having to you have to break all of those hydrogen bonds that are holding water molecules together. So again, this is endothermic, it's positive, heat is going into, so endothermic, because it's positive, heat's going into the system, and this is how much is necessary. All right, I'm going to start you off on the next one, number 3, and then I'm going to have you finish 3 and 4, and then I'll post the answers to it. I'm not going to post the answers with me doing them. I'm just going to post the worked out answers. The only trick between 3 and 4 is the wording. So let's go to number 3. It says, how much energy is needed to change 36 grams of water, okay, from 25 degrees Celsius to steam at 100? So you go, oh, we haven't talked about this word steam at 100. So you go, okay, well, if I'm going to draw my diagram, whoa. Okay, remember this is 0, this is 100. Sorry, it wasn't the best straight line. Okay, and I think we're starting at 25, right? So 25 is like right here. So the problem with 100 is that 100 has 2 locations. It has this corner and it has this corner. So remember, this is solid, this is liquid, This is gas. When you hear the word steam, most likely you think of gas. So if you're going to pick steam at 100, it is going to be this intersection right here. This is 100 where you have gas. So when I go to draw my arrows, I can't just stop here. I also have to move over. Okay. Now, the next problem, number 4, discusses how much energy is needed to change 36 grams of water from, oh, it didn't have this on here. From maybe 25 to 50. Okay, so this shouldn't be an issue. Sorry. So the thing you want to look at is sometimes they'll use the word, okay, well, I want to do, so instead of this one, so this is what number 3 should look like. You should put your equations in. Steam is going to be on this side of it. Now, we haven't gotten to it yet. I thought it was number 4, but I guess I was wrong. They'll sometimes, how they use steam at 100. You can use, so again, this is 0 Celsius. This is 100 because we're just looking at water right now. Eventually, we will move on to other substances. Okay. They will use the words ice at 0 degrees Celsius. So you go, okay, let's say you start at 25 again. So 25, whatever. Well, you have 2 options at 0 degrees Celsius. There's 2 corners. This would be liquid water at 0. This would be solid water, aka ice at 0, right? Because ice is a solid, and this is my solid end right here. This is like as far as you get, and now you've turned into ice to become a solid. So if you see this word ice, you would need to go like all the way over here. All right. If you hear to water at 100 and not steam at 100, you can stop here. If you hear water at 0 and not ice at 0, you can stop here. But you just need to pay attention to the wording. So I would like you to please, after this, I've done this video now, to please try 3 and 4 on your own, and I will post the answers.